We're going to continue our discussion of confidence intervals by looking only at confidence intervals to capture a true proportion. So again, our big idea is we have a population, and it's hard to know what proportion is true about an entire population. So what we do is we draw a sample, like a smaller group. Maybe we're interested in what percent of people would vote for President Biden. So we sample this small amount, we find our proportion of our sample, which we call P hat, that would vote for President Biden, and we use that to make a prediction about the bigger group. Okay, but rather than just saying it's exactly this P hat, we add and subtract a little bit of wiggle room. This wiggle room is known as your margin of error. So if I want to be 95% confident that I've captured the true proportion of my population, I'm going to be looking at the sampling distribution for proportions again, which is our normal curve. We're going to have our estimate from our sample that's in the middle, and we're going to add on and take away from our P hat. And the values that we add on and take away are going to be based on this normal distribution to get our lower and our upper limit of our confidence interval, which remember we write in this form. Okay, in order to use our normal model for our estimation, there's some conditions we need to check. For this Intro to Stat course, I'm not requiring you to memorize these. You just need to be able to cite them in situations. So your sample that you draw has to be randomly selected, and this is so we can make generalizations back to our population. Our 10% condition. Well, whatever sample you draw has to be less than 10% of the entire population when we're sampling from a finite population. Meaning if you only have, let's say, 1,000 people in your population, you can't take more than 10% of them for your sample. And lastly, we talked about this before, in order for our distribution to be approximately normal, we need to have at least 10 expected successes and failures. Perhaps you notice a small difference. We have n times p hat rather than n times p, and that's because we're not going to know our true proportion. That's what we're trying to figure out, so we're going to use the next best thing. That's what we do in stat. Okay, so we need at least 10 successes and 10 failures in order to continue. Again, no need to memorize, just be able to cite them, and I'll show you an example of what I mean by that. So again, some other big ideas about confidence intervals. It's written like this. First number, second number with a comma in between. It's our point estimate, which is going to be our sample proportion. We're going to add and subtract our margin of error. And here's where it gets technical. Okay, so our margin of error is calculated using the following formula. Z star. I'll talk a little bit more about that. Just think of it like your z-score. It works, acts, thinks the same way as the z-score. It's a technicality. It's multiplied by our standard deviation. Well, how do we get that? We did p times 1 minus p. Again, we don't have p, we have p hat. So p hat times 1 minus p hat over the sample size. Okay, this is the formula you will use to construct a confidence interval. So let's talk about this whole z-star thing. Well, if we don't know our true proportion, we don't truly have a z-score, so we call it this z-star. It's called our critical value, but again, it operates just like a z-score. It's the number of standard deviations away from the mean. It gets a different name because we don't know our true mean. We're going to be estimating. All right. What z-score corresponds to the following areas? So if we are thinking about that we want to be, I'm going to talk 95% confident first, since this is the one that we use so often. So that means that 95% of our data needs to be between two values. Well, I'm hoping you remember that we said 68% was within one standard deviation, 95 was within two standard deviations. So most people are tempted just to say, oh, well, the z-score that corresponds to this is exactly 2. But that was an estimate, so we're going to do just a little bit better. There's a calculator function that works backwards to find our z-score. That calculator function is inverse norm. We used it earlier in the year, so take a second, find it on your calculator, hit second vars if you've forgotten where it is, and it's option 3, inverse norm. Select that, and you're going to be prompted for the area first. So your area is 0.99 as a decimal, and then you need mu of our normal curve. Well, for a normal curve, we're going to go to our standard normal where we use 0 and 1. So mu is 0, sigma is 1, and it gives you the choices for left, right, or center. We want the center because we want it, in the center of our distribution. It matches the picture. It's not the left or the right tail. Hit that. Arrow down and hit paste. And what's going to happen is you're going to get 2 z-scores. We're going to use the positive one, okay? So it corresponds to, I'm going to go to 2 decimal places, 1.96. So that's a critical value. Again, I called it a z-score. It's a z-star, you can say it as, or it's the critical value. But it works just like a z-score. So you're going to repeat the process. If we wanted to be 99% confident, that means 99% of our area and is going to be contained within the interval. So that's going to be wider. A wider interval you should be able to see. So again, you do inverse norm. Go ahead, try it on your calculator this time. Oh, and I just realized on the last one I wrote 0.99, but it was actually 0.95, excuse me. I did 0.95, I talked about 0.95, found 0.95, and wrote 99. All right, but for this one, we're doing 0.99, 0, 1, and center in inverse norm to get z-star. That gives me 2.58. Now, if you're not doing this with me, I highly suggest you do. All right. Another more common one is 90% confident. That would give you a narrower interval. So inverse norm, 0.9, 0, 1, and center. And that gives me approximately 1.65 for the critical value you will use in the formula. Okay, so the one you're going to end up using the most often is 95% confident. It comes up most in real life applications, so a lot of kids just start memorizing, oh, it's going to be 1.96 rather than doing it over and over on the calculator. A reminder of the interpretation you're going to use. We are 95%, now that percent might change, confident that the interval from A to B captures the true proportion of whatever it is we're trying to do in context. When I say in context, like the true proportion of people who would vote for President Biden. All right, so one of the things that comes up from time to time, if we want to decrease the size of my confidence interval, like I don't want it to be super broad, one of the things that you have control over is you could ask more people. So if you increase your sample size, you decrease I'll say your margin of error, which would decrease your interval size, margin of error. Okay, so what I want you to do now, it says, what z-star or what critical value would you use if you wanted to build an 85% confident interval? So that means within the normal curve, you want 85% to be within here. So you're going to do z-star is equal to inverse norm, your area is 0.85, mu is 0, sigma is 1, and you're going to do the center. Go ahead, actually try it, see what you get. Hit pause when you're ready, or hit play when you're ready. I get 1.44. Now is a good time to make sure you're checking your understanding. So I have assigned a Khan Academy assignment on critical values. In this, you'll just quickly practice finding your z-star.